Hi everyone, a pleasure to be here. And today I am going to talk about model evaluation. The basics you need to know to understand how your model is performing and how you can evaluate the model of your performance using RoboFlow's feature called detailed model evaluation, which really helps a lot in there. Okay, let's get started. So why is it important to know how a model performs? Of course, we all want to have a good model. Um, But one of the key things to keep in mind is when we train a model, it's trained on a specific kind of data. We also want to make sure that the model works as is expected on new data. So when we use it in production, it performs as expected and we can simulate that. Also, we want to be able to identify certain areas where the model might need some improvement. And to be able to improve it, we first need to understand where is the model good and where is it bad. So we can also use this to compare different kind of models. We can use different model architectures. We can play with the data. And when we have a nice and reliable way to evaluate the data, we can easily compare them with each other. So at the end, we want to support transparency so we know what is the model doing when we put it in production. Um, yeah, so the first thing I'm going to show you, some of you might notice, some might not notice. This is a confusion matrix. Basically, this is the way in computer science, in machine learning to display results of a model evaluation. And I'm just going to quickly explain how it works. So basically on the top, we have the ground truths of the model. So everything in here means um, positive or negative. This means this is what the actual data look like. We can think in an example that makes it a bit easier. For example, we can think of here, a patient or an image is positive for cancer, and here it is negative for cancer. So everything in this column means the real data, the real image is positive for cancer, and here on the right side, it's negative for cancer. What you do here, we predicted on some images from a different data set, for example, and now we want to display that. So we used that confusion matrix, and what we got right here on the top left is all the true positives. That means all the images where the image contained some cancer, it was positive for the cancer, and our model was correctly predicting that. Here, the false negatives are exactly the opposite. So it means in the image, there is some cancer that the model should be able to detect, but it missed that. And what you have here, in general, you have the numbers in here. So you can see how many images of your data was actually a true positive, how many images were a false negative. Also, you have here the false positives, so where the patient was negative for cancer, but our model predicted positive for cancer. And here we have the true negatives, which just simply means patient cancer-free, and our model also didn't ping for cancer. So I will show in a minute how this looks like when we fill in numbers. So as we work in computer vision, it's not as simple as in classification, I would say, where you can say predict label A or predict label B. We work with bounding boxes. So the models often or always predict a bounding box, and the ground truth of the bounding box, which you can see right here, often differs a bit from what the model predicts. So they're basically the same, and the model worked. It like kind of detected the dog, but the bounding box is a bit off. So what we are using to actually say that the bounding box prediction is correct is we use the intersection over union. So we are measuring the overlap between the predicted and the ground truth bounding boxes. Here for model evaluation, this means we use an intersection over union of 30% for the detailed model evaluation feature, which I'm going to show. Here we have our first example. Now we're talking a little bit about the metrics. What metrics are important and where do you have to be a little bit careful? So what you see here on the right side is an X-ray with a brain tumor, which was detected by our option detection model. So this is a public data set which is available on universe.roboflow.com. So let's have an imaginary example. Let's imagine the following. In our data set, we have 95 images without cancer and 5 images with cancer. And now we're using our model to predict on these images. And this is the outcome, basically the confusion matrix, but written down as a list. So 90 of the 100 images were correctly identified as not having cancer. We have 5 false positives, which means there is no cancer in the image, but our model incorrectly identified this as cancer. We have 1 true positive, 1 cancer that was correctly identified out of the 5 images which actually contain a tumor. And we have 4 false negatives. That means we had a tumor in the image, but it was incorrectly identified as no cancer. There is the basic metric that often is used that is called accuracy, which is basically just saying, okay, we have 91 correct predictions. When we watch here, like 90 images with true negatives were predicted correctly and 1 true positive, which means 1 which had cancer was also correctly identified. So that means we have like 91 correct predictions divided by all predictions, which leads us to a model's accuracy of 91%. One might think, wow, that's amazing. Our model is correct in 91% of the cases. But what's happening here is that the data is highly imbalanced. This means we have kind of a prediction bias. So if you would imagine a model that always predicts like no cancer, will achieve an accuracy of 95% in that case, even though it didn't identify any true positive case for brain cancer. So in that case, and in many other cases, accuracy is not the right thing to evaluate a model. So it can be very misleading. Just give me a second. Going to show that in a second. So what we have here is how we do it in RoboFlow and how you should also do it when evaluating your model's performance. We have the same example, but we're using some different metrics to evaluate them. One is called precision, one is called recall, and one is the F1 score, which is basically a balance between precision and recall combined into 1 score. So precision basically means when the model predicts brain cancer, how likely is it going to be correct? So we are ignoring how often it missed something, but when it's saying this dot right here is brain cancer, how often is it correct? And in this case, as we missed quite a few, misclassified them, as we have some false positives, this is only 16%. So it's not very likely to be correct. So low precision means we will have many false alarms. The second thing is recall. Recall is also a very important metric. It means that the recall basically helps us to ensure that the model identifies as many actual cases of brain cancer as possible. So if we have a very low recall, as we have it here right now, it means that we missed a lot of brain cancer. For example, imagine we didn't have a bounding box here and our model missed that. That is because we have a very low recall. So what is important here, and what I wanted to mention as well is it's very hard to get a perfect model, and the model also doesn't have to be perfect always. It's more important to focus on the right metric that is important for your task. For example, in this task here, the most important thing is to have a high recall, so we don't miss any cancer. If we have a few false positives, which means our precision goes down, it's okay because a doctor will check anyways. But we want to have a very high recall so we don't miss any kind of cancer. The last thing of this theoretical part, and then we dive right into the app, is data set splits. As you might have noticed on RoboFlow, you can split your data into train, valid, and test set. And this is a very specific reason. The reason is that we use the train split for converging the model using a loss function. This means we're using this data to train the model. The model tries everything it can, so it correctly predicts the training images. So what will happen? The model will overfit. That means the model learns overly specific on the training data, but does not generalize well on images outside of it. So what we do here, we introduce a validation split. So we take some part of the data, around 20%, and we use it during training. But we don't train the model on it. We use it to check our model on the validation split during training to see when we reach the point where we are getting too specialized on the training data. So we have some data outside of it that we don't use for training, and we use it to check. And you can see it right here, overfitting in training. A lower number means better because we're getting, that's the training loss basically. And as this goes down, here on the training set, this is how the model learns, and it gets better and better. And you notice right here, here's the validation loss on the validation set. So right here, the model doesn't get better anymore on the validation set, which means here is the point where overfitting will start and we get too specialized in our training data. The last thing here is the test split. To really, really, really evaluate a model's performance, we need to have a third kind of split, the test split, which the model hasn't seen before. It's quite common to also use the validation split because the model was not trained on it, but it used it during training. So you have to be a little bit careful here. But the most important thing is do not evaluate performance on training data on the train split. You do it on the test split, have some separate data outside of the training data. And if you have very little data, you can also use the validation split. So let's hop into the app. So on RoboFlow, we have a cancer detection data set, which we have here. We have a trained model for object detection, and we basically have one class in this model, which is tumor. So we're trying to detect tumors in here. The feature detailed model evaluation, which we automatically run on every model that is trained on RoboFlow, can be found right here. We open it up, and the first thing you see is the confusion matrix, what I introduced to you before. So you can see right here, we have basically the true positives, tumor. This is the cases where there actually was a tumor in the image and the model was able to predict it correctly. The false negatives are the ones that were missed by the model. And the false positives are where we incorrectly classify the tumor where there were no tumor. One of the great things here, you can see precision and recall directly on top. What we notice is precision is pretty good. So in 90% of the cases, when we say it is a brain tumor, it is actually a brain tumor. But our recall is little bit low. That means we will miss around 20% of all the brain tumors in the X-rays. So what we can do here, we can drag down the confidence threshold. That means the confidence basically is something the model uses to communicate how certain it is that a certain prediction is correct. And here, the predictions you can see right here, the model is certain above 50%. So when we drag that down a little bit, what happens, you can see here, as we decrease the confidence, also some predictions where the model is not quite certain, around 30, 40%, are also used. So our recall goes up. This is like one important thing. So as we want the model with high recall, what we can learn here is that we can decrease the confidence threshold when we infer on the model on production to increase our recall because we care mostly about that. Of course, we also want to have a high precision, which gets lower, of course, because we have much more false positives. But this helps us get a nice recall. And what I can show you as well is you can click on here and see what kind of images, for example, are the false negatives. So you can really go into detail and see what is happening here. So right here, we have a tumor that was marked as being here. But our model predicted that the tumor was right here. So one could say, okay, at least it got the tumor. It classified some tumor in this image, but it's on the completely wrong spot. And then we have to think about is if object detection is the right thing here to do, or if we should use a classifier on the image. So very interesting to see that. And what I also wanted to show is, right, drag the confidence threshold a little bit down and go here to the vector analysis. This is also a very interesting tool. Here on the bottom, we have the valid and the test set selected. As I said before, one could also use the training set, but model has seen this data already. So I'm going to put that away, also using only the test set. And going to drag the F1 threshold, as we learned before. That's a metric that uses precision and recall, dragging it a little bit down. So this makes it very easy for me to see what kind of images have a bad F1 score. Here on the vector analysis, what we do here, you have images, I can select one, and we calculate clip embeddings for every image. So images, clip embedding is basically a description of the image put into a vector space. So images that are very similar will be grouped together in here. So this is very helpful to find some stuff that goes wrong in the model, because we can just simply select the images which have a bad F1 score, and these seem like they belong together because they're grouped together. We can go in here and see like, okay, so we have as our ground truth the tumor in here, and the model prediction basically predicted 2 times. So this is because we decreased the confidence threshold. So this is what is going to happen in production. Right here, we have a ground truth that looks like this. Model prediction like this. And yeah, so what we can conclude from this right here is that we should consider lowering the confidence threshold when using the model in production, so we are sure to not miss any cancer. We also had a few false negatives that I showed where we completely missed the cancer. So it would be really good if we could add more of these examples into our training set and train a new model, because now we can really see on which images does our model perform very bad, so we can use those. And we also saw that like on some images, the predicting bounding box was kind of not correctly right, because we used this intersection over union of 30%, but it still kind of predicted cancer. So we should ask ourselves the question, do we care about the location of the cancer? And if the answer is no, if we just want to classify is cancer present or not, we can consider using image classification, which you can also simply do on RoboFlow. As we are already halfway through or even longer, I'm going to quickly skip to another model that I'm going to show you. This is a rock, paper, scissors model. Basically, what it does, you can see it right here. It predicts what the person's hand is. Is it a rock, a paper, or a scissor? You can see it right here. And what I wanted to show you in here is now the confusion matrix gets a little bit bigger because we have many more classes. We have a paper class, a rock class, and a scissors class. And what the confusion matrix here is doing, it's plotting every prediction class against every ground truth class. So what you can see here on this diagonal, you can also see it here in the explanation on the right. It gives us a super nice and super clean and super easy way to see where our model performs well and where it doesn't. For example, here we have a lot of cases where our model was able to predict paper correctly. We can select these and see all these cases. What I noticed here, for example, we have some cases where our model predicted misclassified paper as scissor. So we are going to take a look what is going on in here. So this is actually paper. but our model is predicting scissors. And so we can see really well, okay, they might look a little bit similar. As you can see here from the fingers, it could also be like some sort of scissor motion. And when we step this up and go to the next images, you can see they all like are pretty similar. This could also be like a scissor. Um, this is also the ground truth says it's paper, but it's also like pretty similar to a scissor. So what this tells us is when we want to improve our model, um, we should make sure that our training data is labeled correctly, but also um, when there are some examples like here where it's pretty similar, we can use more training data to fix that. So let's jump right here. So what we saw is that this is a very good model. We saw some good precision, good recall. Um, Also, some bounding boxes were missed. Oh no, some bounding boxes were not like really correct, but the most important thing is we should add more examples of papers and scissors to like distinguish a little bit better between them. One thing that I also want to show you is what we didn't see right here because I skipped through it because we're running out of time is model evaluation can really help you remove mislabeled images. We're seeing it again and again. That when you label thousands of images, some errors might sneak in. And what you can see here, this is a pothole detection model. And the ground truth looks like this. You can see we have some potholes up here which were not labeled. But what the model predicted, and we only found this because of the model evaluation, it predicted some potholes up here. And this tells us like this data is mislabeled. So we should really be like labeling this data here, then our matrix will also improve and our model also gets better, of course, because the model is already assuming that these are potholes because it learned it. Yeah, so one thing that's also like really nice to see is, for example, I have a tennis ball detection model right here. And what it does is like it tries to predict a very small ball on a tennis image. And you can see here recall is really low. Precision very high, which means when our model predicts a tennis ball, it's very likely to be correct, but it misses a lot of balls. You can see it right here. We step in here, like the ball is basically super small. So the model is not able to predict that correctly. And if we step here for all the images, we can see here we have the tennis ball. Looks like this when we zoom in. The model just missed it because it is too small. And as we saw this and used model evaluation to step through everything in here, we can tell the following, like our precision is good, as I said, recall bad. So we could add more data and train a better model, but also, as we now know that the problem is probably like small objects, we can use slicing aided hyperinference, which is a computer vision method, which can improve detection accuracy for small objects. Basically, what you're doing there, you slice an image into multiple slices. That means that our object that we want to detect is a little bit bigger in that slice. And what you can do with RoboFlow, I have it right here. This is our low-code solution called Workflows, where you can drag in some computer vision blocks. And it might sound a little bit complicated, slice the image in different parts, then predict the balls on it, slice it back together, put the predictions together. But what you can basically do is right here, you can put an image in this pipeline. You can drag a block in here, which called this image slicer. It automatically slices your image. You can run our tennis object detection model on it, and in the end have a block that stitches it all together. And this will improve performance very much when you watch this matrix right here. I did that on my model. And what I got was 97% precision and 82% recall, and that's a model that I can use in production. So that's very nice. So the conclusion here is really pay really look on what you're trying to evaluate. Do you want to have a high precision, and when you make a prediction, it should be correct, or do you want to not miss a prediction, so you want to have a low recall, a high recall, or is both important? Then you could, for example, use an F1 score. Using a detailed model evaluation and a model evaluation in general, it really helps you understand which classes perform well and which don't. And as we saw with the cancer detection data set, the optimal confidence threshold plays a big role how your model performs in production. With the vector analysis, you can find some clusters in your data as similar images are grouped together, and you can see which clusters perform well and which don't. We also saw that it really helps with finding and fixing mislabeled data. And the most important thing, you can identify problems. For example, small object detection. We know in computer vision there is a method called SAHI. Once we identified the problem that the objects are just too small, we can go a step further and fix those. And with that, I want to finish the presentation. Thanks to you all for coming and happy to answer any questions. Thanks.